Welcome to Chapter 9. We're doing chemical bonding, Part 2. So what we're going to do in this chapter, we've already talked about how to draw Lewis structures, but we're going to assign the molecular geometry, and we want to be able to describe that in more detail than what we have been doing when we just introduced how to draw Lewis structures. And so you can go back and look at how to draw Lewis structures, because we're not going to be talking about that. We're just going to go straight into those Lewis structures, and then we're going to talk about the molecular geometry. We want to assign the dipole moments based on the electronegativity differences and decide if a compound is polar versus nonpolar. And then we want to talk about bonding theory. So there's valence bond theory, there's hybridization, and then we're going to talk about molecular orbital theory. And so we're just going to talk about those little overlaps, and we're going to apply those checkpoint problems. So we'll be working the checkpoint problems in this chapter. All right. Now, so let's start with the electron domain geometry and molecular geometry of CO3 2-. So this is carbonate, and you first want to do your connectivity where carbon is the center. You want to calculate so this is your connectivity, your total valence electrons. So carbon has 4 because it's group 4. Oxygen has 6, and there's 3 of them. And then your charge is a -2, so you got to add 2 electrons. So we're trying to get our total electron count. And so if you add this up, you have 18 and 24 valence electrons, and you can go 1, 2, 3, 4, and you're going to have 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Let's count this up. 8, 16, 17, 18, 19, 20, 21, 22, 23, 24. And if you do your formal charges, you'll see that each oxygen here has the negative charge. So this is the structure. Like I said, I just went to the shortcut for time purposes. Now, we need to assign a thing called the electron domain. And so you look at your central atom and you say how many things are bonded to that central atom, and you see you have 1, 2, 3. So you have 3. And so if you look, and you should memorize these because you're not going to have this sheet for your final exam or even your exam 3. But this would be 3 electron domains, and that would be trigonal planar. And so you see that right there where the trigonal planar electron domain and the molecular domain are the same. And this happens when there are no lone pairs. So there's no lone pairs on carbon. So that means that the electron domain will equal the molecular domain. And so they're both trigonal planar, and that answer is D. Okay, let's go to 9.1.2. What are the electron domain geometries and molecular geometry of ClO3-? So here we have the connectivity where chlorine is your central. There's 3 oxygens. We've seen this. This is the chlorate ion that you memorized. If you add up your total valence electrons, chlorine has 7 because it's group 7. Oxygen is 6, and there's 3. And your charge is a negative, so you add 1 there. So that's 18 plus 8 is that 24? Yeah, so here we have, and I see that you have 1 negative charge, so I already know that this is going to be, oxygen is going to have 2 bonds and 2 lone pairs. It might take you some time to work through that. Chlorine is greater than row 3, so it's greater than 3 or equal to 3, so it can do an expanded octet. And that means it can have more than 8, so it has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Okay, and so this is maybe not the one that they did. So there is a resin structure, which that means these are equal. That means a pi bond here could be a single bond, and that means you would get a lone pair on the chlorine. Well, I guess we should just do it the way that you put all the oxygens on there and you work outward, inward. So it would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. And then you'd have, let me count that again just to make sure. Is it 24? 8. Wait, I think I have them wrong, don't I? 8 plus 8 is 26. Okay. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. So let's go back to here. We have 26. So make sure you always do that. I think they want you to have a lone pair. So let's, like I said, there's resin structures here. And one of the resin structures would be, so you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. And you would see that the formal charge for chlorine should be a +1. So it's group 7 minus 1, 2, 3, 4 bonds minus 2 dots. So that's 3 minus 2 is a +1. So that would give that a +1. And so the overall charge is a negative. And then you have to look at what are the 3 things. You have 1 group here, 2 group, 3 group, and then this lone pair is a group, a thing. So that's 4. And so if this has 4 electron domains, to use the words of the book, the electron domains, that's tetrahedral. Now the molecular geometry will cause this lone pair to push these bonding groups, these oxygens, far away, and so that would push these down, and then you'd have your oxygens down here. And this is the molecular geometry, then would be trigonal pyramidal. And so if you could try to memorize that, that would be nice, so you could see that the VSEPR, the valence shell electron repulsion, changes that molecular geometry. Okay, the other thing that we need to talk about are bond angles.
No.
And then we're going to talk about molecular. So let's look at 9.1.3 for the bond angles. And what we have here is acetylene. Acetylene is the gas that burns for welding. And so you look at this carbon here and you say how many bonding groups are there. There's 1, 2, 3, so, or electron domains. And there's 3 of them. And so that's trigonal, planar. There's no lone pairs, so molecular geometry is the same. And now, based on the degrees between this group and that group is always based on the electron domain, okay? And so this is going to be less than 120 degrees. If this had been a hydrogen, then it would have been exactly 120 because it's based on carbon hydrogens, but because this is a carbon, everything's going to be less than 120. So what you do for bond angles is you memorize them. So if you have like tetrahedral, it's 109.5 degrees. For trigonal planar, it's always 120 degrees. And so anytime you have those groups, it's always less than that. It's less than 109.5. If you have something that's linear, that's 180, right? And then if it's bent, it all depends on the electron domain. So the electron domain determines the bond angles. So let's look at another one. What is it, 9.1.4? We have oxygen and we have two lone pairs. So when you look at this, you see that you have one group, two group, three, four groups. So you have 4 electron domains. And so that is tetrahedral for the electron domains. But because you have 2 lone pairs, right here and here, that is going to push those 2 groups down, and that's going to be bent. And so I can look at that and always double check. And what that would be is, okay, so you have 4 groups. So you see 4 is tetrahedral, and then you have it's an AB2 with 2 lone pairs, and it's like water, and that's called bent for the molecular geometry. Now, the bond angles, though, okay, is based on your electron domain, and tetrahedral is always 109.5, so these are less than 109.5. So these are less than 109.5, and that's exactly the right answer, C. All right, so let's push on to the next topic, which is the polarity. So we need to talk about the molecular geometry and polarity. So here we want to show the electronegativity difference within a covalent bond. Remember, a covalent bond is a line where they're sharing electrons, and electronegativity increases going up a group and going towards over the row to the right. So that's increasing electronegativity, and we'll draw a dipole. So we'll draw something with a positive and an arrow, and the arrow is representing the 2 electrons and then pushing towards the more electronegative atom. And this would be your delta positive, and that would be your delta negative. And you do this for each bond, each covalent bond around a central atom. And then what you do for the compound, decide whether it's nonpolar versus polar, is you add up all the vectors. And if it has an overall vector, then it's going to be polar. If it has no, then it's nonpolar as a molecule. So it says, identify the polar molecules in the following group. So we have HBr. So if you draw this, Br is more electronegative than hydrogen, so it's going to, that bond's going to push towards the Br. CH4, this is tetrahedral, each one of these bonds are going to push towards the carbon, but because they have symmetry here, it's going to cancel out, and that dipole will be 0D. D stands for di. And so this is polar. This would be nonpolar. And then we have CS2. And folks, I'm going to have to add up my total valence electrons. I got carbon is 4, sulfur is 6, there's 2, so that's 12. 12 plus 4 is 16. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And so that is linear, and that's going to pull towards the sulfur, and they're going to be equal, so that's going to be nonpolar. So what's the question asked for? The polar molecules, so it's HBr only. So that's A. Okay, let's do the next one. The next one, it says identify the nonpolar molecules. And we have SO2, we have NH3, and we have the Xeon F2, the Xeon difluoride. And so sulfur is 6, oxygen is 6 times 2, which is 12. So this is 18 valence electrons, and we put, so that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay, so there we go, and you got to look at your molecular geometry. So you have 1, 2, 3 groups. So 3 groups, the electron domain would be trigonal planar. Okay, but because you have an AB2 with 1 lone pair, so if you look at that, you have bent. So when you draw that bent, this electron pair will push down these oxygens. And so when you look at this, between oxygen and sulfur, it's going to go towards the oxygen. And so you're going to have an overall, it's going to be overall polar. And it was nonpolar. Okay, so here we have nitrogen. And if you draw this molecular geometry, you're going to see that it is, so it goes from tetrahedral for its electron domain. But then because you have this 1 lone pair here, it's going to push everything there. And this push, these groups together, the molecular geometry will be then trigonal pyramidal. And the it would all push this way, so you'd have an overall dipole. So this would be polar. And you're going to find that that means that these molecules will dissolve, they'll be soluble in polar solvents. And a polar solvent is like water. So that's what we're looking at, is to be able to predict these properties. And so their polarity determines this. So Xeon has a valence electron of 8. Fluorine is 7 times 2, 14. So that would be 22 valence electrons. And so this fluorine is at the top and the bottom, and then you have your lone pairs. So let's look at that. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. And what happens is the fluorine is going to pull, let's say, to the south pole, and the fluorine from the north pole is going to pull. You have symmetry. Whenever you have symmetry, you're going to find that this is nonpolar. And so the answer is which are nonpolar, and it's C. So if you do another kind of an always, whenever you have 1 lone pair, a single lone pair, you can always go ahead and assume that it's going to be polar. Okay. So, okay, now we're going to go on to the bonding. Let's go on to hybridization of atomic orbitals. And I will go to the checkpoint questions here. So I'm on 9.4.1. How many orbitals does a set of sp2 hybrid orbitals contain? So how many orbitals does a set of sp2 hybrid orbitals contain? Okay, contain. So what happens here is you got to look at like the first row. Hydrogen and helium. They only have 1s orbitals. An orbital is just the S shape, probability, the cloud, the electron cloud in which you're going to find an electron. They only have 1s orbitals. But you come down to the second row. And the second row has the 2s, and then they have the 2p, and we have 2px, 2py, and 2pz. And we've learned that these are the s, and we learned that this is a dumbbell shape like that. Okay, but what happens is hybridization came about because really you couldn't explain the tetrahedral. The tetrahedral with the 109.5 degrees bond angles should be like 90. So the only way that the 109.5 degree bond angles can be explained is through this thing called hybridization. And what happens, you can think of these as shape changers. Okay, so instead of just putting electrons in a sphere or electrons in a dumbbell, probability cloud of finding electrons, what hybridization do, like second row, since you have all these S's and P's, you can change the shape. And so a set of sp2 combines one S and combines two P's. So let's combine that P and that P. And so we are combining 3 atomic orbitals. Okay, so we have 1, 2, 3. So, and we're going to call that shape now we're going to call it an sp2 shape. So we'll call this an sp2 shape, and we're going to have to give it a different shape. And so those atomic orbitals are 66% P and 33% S. So if you were to try to draw something new like that, you'd have to draw it kind of what I call like a wiffle ball bat. Instead of like a dumbbell, you have kind of more of a fatty end here, and then, but it still has more of a kind of a bat shape. Okay, so this is like that. And because you have 3 of them, you threw in 1, 2, 3, and you have now a new shape, but you put in 3. So now you got to get 3 out. So we're going to need 3 of these. Okay. So these wiffle ball bats, we're going to have, so if you add your superscripts. So sp2 is 1 plus 2 is 3. So we need 3 of these. 1, 2, 3. So the answer is 3. And what that does is that leaves 1 left over. This is unhybridized P left over. And that's going to be important for multiple bonds. You have to have that for a double bond or a triple bond. Okay, so if you have 1, then you can have a double bond. You have to have 2 unhybridized P for a triple bond. So what is this? An example of something like this would be this compound here. Okay, so this is formaldehyde. And how many things, this is what you want to ask yourself, how many groups, things is your central bonded to. Okay, so we have 1, 2, 3. And so if you have 3, then you need these hybridized orbitals. And they would be a shape like that. 1, 2, 3. And you know if there's 3 electron domain groups, and there's no lone pairs on this carbon, that is trigonal planar. And that means that each one of these groups are 120 degrees less than 120 degrees apart. So we're just describing the shape, but in order to get this shape, we had to hybridize, because you can't just get this shape with an S and a P and another P. You have to actually do like a shape changer and make new shapes. And so this is a wiffle ball bat type shape in order to get this. And also notice that you do have a pi bond here, and you can have that because you have this unhybridized p orbital. So the answer is B, 3 atomic orbitals. You can just add your superscripts on that. Okay, let's go to the next one, 9.4.2. How many p atomic orbitals are required to generate a set of sp3 hybrid orbitals? Okay, so if we have sp3, so let's go back to like row number 2. Okay, so row 2, you have a 2s, a 2px, a 2py, and a 2pz. Okay, and now it's asking for how many p atomic orbitals are required to generate a set of sp3. So you're going to have to combine one s, 1p, 1p, 1p. You're going to have to combine the s and that one and that one and this one, and you're going to have new shapes, and those new shapes are going to be an sp3. It's going to be 75% p shape and 25% s, so it's going to be kind of a skinny wiffle ball bat. And you're going to have add your superscripts, 1 plus 3. You're going to need 4 of these. So we're going to need 4 of these skinny wiffle ball bats. We'll call these skinny wiffle ball bats. Bat shapes. Okay, so I'm just showing you that, so how many p orbitals are required? You're going to have all 3 of them, 1, 2, 3, to get this shape. And you're going to have to add the superscripts. Now, why is that important? Well, what compounds will use an sp3? Methane. So methane has, you got to look at your carbon and see that it's bonded to 4 groups, 1, 2, 3, 4. So we have 4 things, 4 groups bonded to our central carbon. So we need those shapes to be able to do this. We need the sp3 because the superscripts have to add up to the things. You see? So you're going to have to add those superscripts, and that's how many things that are bonded. So this is sp3, and you always will remember that sp3 is tetrahedral, and that's a 109.5 degrees. And that describes the shape. All right, so let's go on to hybridization and multiple bonds. So now we're looking at 9.5.1, and which of the following molecules contained 1 or more pi bonds? Okay, so nitrogen, if you draw its Lewis structure, you would get this. Chlorine. So the way you want to always do these is to first draw a correct Lewis structure. And that's why we talked about that right off the bat. Before even starting this chapter, that's methanol, and then carbon tetrachloride is this. Okay, so now when we're talking about geometries, we care about the central atom. This one doesn't have a central atom. This one doesn't either. This one does. This one does. And this one has 2 central atoms. But the question was 1 or more pi bonds. So all of these bonds here that I'm doing in red are called sigma bonds. And sigma bonds have to have S character. So this is called a sigma bond. Sigma bonds are single bonds, and they require S character. And they hold 2 atoms together. 2 atoms are held together. And they've got to be held between, those electrons have to be between those nuclei. Now, it asks for 1 or more pi bond. This is a pi bond, and this is a pi bond. And so this has 2 pi bonds. Pi bonds are multiple bonds. This one, CO2, has 2 pi bonds. But this one has what we call a triple bond, and this one has a double bond. And none of the other ones do. So your answer to that would be A and C. And we are in agreement. Now I want to tell you about hybridization. The hybridization for these, if you want 2 pi bonds, then you have to have like a PY and a PZ. So the hybridization is an SP. And so what happens is this is a fatty wiffle ball bat. Okay, because we're talking 50% S and 50% P. And then we're talking that's in a single bond. So it's going to be really fat. Really going to have some of that. And you have to have 2 of them. And so that would be like one of your nitrogens there, and it would overlap with another one here. There's your nitrogen, and this would be your nitrogen. And that's your single bond. And so it would have 2 of them, because you'd have your lone pair over here. And then what's happening is you have these unhybridized p orbitals that are like dumbbell shapes. So this like could be your py, and you'd have 2 electrons here. So that's representing 2 electrons. And then you would also have it on the y coming at you front and back, or you could say pz, and you'd have 2 electrons there. And those are the pi bonds. So pi bonds are in the unhybridized p orbitals. And sp, you should memorize that. That is linear, and that means these nitrogens are 180 degrees apart. And the same thing here with carbon dioxide. Carbon, these sigma bonds, and it's linear as sp. And so anytime you have linear, why? Well, how many things does carbon have bonded to it? 1, 2. Well, add your superscripts. 1, 2. So that's sp. 1, and you got to count that lone pair, 2, sp. If you want to figure out what this one is, this oxygen, you have 1, 2, 3, 4. It's tetrahedral, sp3. So you would have to have 4 of those, sp3. Add your superscripts. 1 plus 3 is 4. You have 1, 2, 3, 4. This carbon is an sp3 because there's 4 things. 1, 2, 3, 4. Add your superscripts. And you'd have to have 4 of those because you need 4 of these skinny wiffle ball bats to make your sigma bonds to each one of those chlorines. All right, so now we're doing 9.5.2. From left to right, give the hybridization of each carbon in the alene molecule. So let's draw this out. I think it's actually kind of interesting because it's actually in 2 different planes. All right, so let's just look at the first carbon and let's see how many things. 1, 2, 3. So we have 3 things or groups. Okay, onto that carbon number 1. And so let's add our superscripts. sp1 plus what gives you 3? 2. And we have to have 3 of those, sp2 and sp2. So if you actually look at the hybridization, you take 1s and you have, you have 3 p orbitals. But in order to make an sp2, you had to take this s, you had to take 2 p's. And so you had to combine these to make sp2. And then you're left with an unhybridized p orbital, and that is your multiple bond there. That's your double bond. The double bond goes into that pi bond. Pi. Okay, so here we have the next carbon. So let's count how many things. We got 1, 2. So this carbon number 2, has 2 things. And so you would do S and a P. 1 plus 1 is 2. And since there's 2 things, you'd have to have 2 of these. And you would have 2 pi or unhybridized p orbitals left over. And that's why this carbon can do 2 bonds, 2 pi bonds, because it only used an S and 1 p. What's left over was 2 p's. And when you have the leftover unhybridized p orbitals, you can have these multiple bonds here. Okay, and then let's do the last one. Okay, see carbon number 3. And we have 1, 2, 3 things. So we're doing sp2, because 2 plus 1 equals 3. And now it said from left to right, give the hybridization of each. So we have an sp2, we have an sp, and then we have an sp2. And so sp2, sp, sp2, is that C? Yes. So C is the answer. Don't worry about 9.53 or 9.54. Okay, let's go on to a thing called molecular orbital theory.